Modern engineering is defined by precision. Today, creating a level surface requires advanced laser systems, satellite positioning, digital sensors, and constant recalibration. Entire teams monitor measurements down to fractions of a millimeter. Even with this technology, engineers rarely claim perfection. They aim for acceptable tolerance, not flawless alignment. Precision, in the modern world, is difficult, expensive, and never guaranteed. Despite all these tools, structures still shift. Materials expand and contract. Foundations settle. Tiny errors compound over time. Engineers expect this and design around it. Maintenance is assumed. Reinforcement is required. In modern construction, absolute stability is considered impossible. And yet, evidence exists that challenges this belief. Concrete cracks. Steel bends. Buildings slowly drift from their original alignment. This isn't failure, it's physics. No structure is immune. Modern engineering accepts imperfection as inevitable, which makes one question unavoidable. Why do some ancient structures refuse to behave this way? Across the world, ancient foundations exist that remain astonishingly level. Not symbolically, not approximately, but measurably precise. Built thousands of years ago, these structures show minimal deviation, even today. No machines, no digital tools, no modern instruments, only stone and accuracy that shouldn't exist. Consider the Great Pyramid of Giza. Its base spans more than 13 acres, yet the variation in level is less than a few centimeters. This isn't legend. It's been measured repeatedly with modern equipment. Engineers openly acknowledge the precision, even if they struggle to explain how it was achieved. To replicate this today, engineers rely on satellites and laser arrays. The ancient builders had neither. Still, the pyramid's foundation remains remarkably flat. The margin of error is so small it rivals modern construction standards. This isn't coincidence. It's intentional design, executed without modern technology. There is no evidence of advanced machinery, no surviving blueprints, no written manuals explaining the process. Yet the result speaks clearly. The precision exists, even if the method does not. And this pattern is not isolated to Egypt. High in the Andes Mountains, Inca builders achieved something equally disturbing. Massive stone platforms laid across uneven terrain, perfectly balanced and stable. The elevation changes are extreme, yet the structures remain level, even after centuries of seismic activity. The stones themselves tell another story. They are shaped with such accuracy that gaps are nearly invisible. No mortar, no filler, just stone fitted to stone with extraordinary precision. Even modern cutting tools struggle to reproduce this level of fit consistently. During earthquakes, these walls move. Then they settle back into place. They absorb energy instead of resisting it. Modern engineers study this behavior today, still trying to understand how ancient builders achieved such resilience through geometry alone. Now shift to ancient Rome. Their aqueducts carried water across miles of terrain. The gradient had to be exact. Too steep, and the flow would destroy the structure. Too shallow, and the water would stagnate. Yet the balance was maintained across entire regions. Surveying such gradients today requires precision instruments and constant recalculation. The Romans relied on observation, experience, and methods that remain poorly documented. The result? Water systems that functioned reliably for centuries. Engineering tolerances exist because perfection is assumed impossible. Ancient structures challenge that assumption. Their measurements don't drift. Their alignments persist. They behave as if they were, designed with an understanding of error control we still struggle to match. Egypt, Peru, Rome, different cultures, different eras, same precision. This consistency suggests shared understanding, or rediscovered knowledge, rather than coincidence. Modern engineers rely heavily on machines. Remove the tools, and the system collapses. Ancient builders had no such safety net. Their success depended entirely on method, not automation. Modern precision is fragile. It requires calibration, power, and constant oversight. Ancient precision appears stable. Once achieved, it endures. There are no surviving technical explanations, no equations, no instructions. just structures, standing silently, resisting time. This creates a paradox. Precision without technology, engineering without machines, knowledge without documentation. Something doesn't align with our assumptions about progress. Ancient builders were not guessing. They were calculating, even if their math looked different from ours. Their intelligence was practical, observational, and deeply refined. Too often, these achievements are labeled symbolic or ceremonial. But symbols don't measure millimeters. Engineering does. Some researchers suggest astronomy, aligning structures using stars, shadows, and seasonal movement. No machines, only precision observation. Others point to water leveling, a simple principle capable of remarkable accuracy when used correctly. Elegant, reliable, overlooked. This knowledge may have been passed orally, master to apprentice, refined over generations, then lost. When methods disappear, only results remain. And without context, we underestimate the builders who created them. Why is this rarely discussed in engineering terms? Why avoid the implications? Perhaps because it suggests progress isn't linear, that some knowledge can be lost, not replaced. Modern structures demand constant repair. Ancient ones endure with minimal intervention. Stone placed thousands of years ago remains aligned, quietly defying expectation. What if ancient builders mastered principles we've since abandoned? What we call advancement may simply be reinvention. These foundations remain, perfectly level, and they ask a question we still can't answer. If the past achieved this without our technology, what else did it know?